Welcome back to Integral Calculus. In this video, I wanted to talk about rate of change applications. Rate of change is probably the most important application of the derivative. And for a lot of purposes, you can think of rate of change as the meaning of a derivative. There's a couple of places later on in the course where that kind of logic is going to become important. So just as a way of reminding you how those basic ideas work, I want to go through a couple of classic examples. Let me get my head out of the way, and I'll start off with, say, kinematics. If you are talking about the position of an object, and you call it the function x of t, well, the rate of change of position with respect to time is velocity, or speed. So x prime of t is the change in position over time, that's velocity. And then the second derivative, the change in velocity with respect to time, is called acceleration. And if you've taken an introductory physics course, that's probably where you stopped. Depending on where you took calculus, you may have kept going, because when I teach differential calculus, I really love to extend it out to the third derivative. The change in acceleration over time is called the jerk. Right? That's something that in everyday parlance you are very familiar with, although you don't tend to think about it in terms of kinematics. Right? If you are in a car and somebody is very aggressive with the gas pedal and the brake pedal, you might feel like you are being jerked around because the acceleration of the car is changing very rapidly. I want to go one step further. I've never seen an application where this is actually useful, but I wanted to remind you that when you get beyond the fourth derivative, or beyond the third derivative, so the fourth derivative or later, the primes start to get confusing enough that you go cross-eyed. So instead of making you count all of those tick marks, we put the number of them in parentheses. So the fourth derivative of position would be the change in jerk with respect to time. That is in fact called the snap. Again, something that in everyday language you are familiar with, right? The snap of a towel. If you whip a towel out and then snap it back, it will create a sound. And if you are even more aggressive with it, you might have a quickly changing snap with respect to time, which is a crackle, right? The crack of a whip, literally there. And if we have snap and we have crackle, I am not kidding, I am not making it up. The change in crackle with respect to time is in fact called the pop. I've never seen an application of it, but it exists and it has a name. So there we have it. Kinematics is a nice place to think about it because, yeah, the stuff down here, weird, probably not things you're familiar with, but up here, right? The position of an object, having a position change with respect to time, having a speed change with respect to time, these are things that we deal with on a regular basis if we have to move around. And specifically, we think about numerically if we ever have to get into a car. There's no reason that we have to think about a position changing with respect to time. We could just as easily be talking about stock market prices and talk about the rate of change of the value of a stock, or how quickly that rate of change is changing, and talk about the acceleration of pricing. We can bring this into many, many other fields, and the same ideas still tend to work. There's a couple of different ways we can go about examples on this. I'm going to do the hard one myself. Get my head back out of the way. Consider a spherical weather balloon being inflated by a pump moving 0.35 cubic feet of air per minute. How fast is the radius of the balloon increasing? Well, in order to solve this problem, we need to know the relationship between the rate of change of the volume of the balloon and the rate of change of the radius of the balloon. And while I highly doubt that anyone has any reason to have thought that memorizing such a formula might be useful, you should be very familiar with the formula relating the volume and the radius themselves. Because we are assuming that the weather balloon is spherical, that means that the volume is 4/3 times pi times the radius cubed. If I differentiate both sides of this equation implicitly with respect to t, right? The volume is a function of t. 4/3 is a constant. Pi is a constant, but the radius is also a function of t. So when I take the derivative on the left-hand side, I just get v prime of t. On the right-hand side, I get, well, 4/3 is constant, pi is constant. A constant multiple doesn't change the derivative. And then we take the derivative of radius cubed, and that will be 3 times the radius squared times the derivative of the radius. Right. I've got a 3 here and a 3 here that are going to cancel each other out nicely. So let's also suppress the of t now because that's a lot to write in. V prime is going to be 4 pi times r squared times r prime. Rearranging that formula, I can write that r prime is v prime over 4 pi r squared. And let's see, we are given that we're dealing with 0.35 cubic feet of air per minute. Right, well, cubic feet per minute is the rate of volume with respect to time. That would be v prime is going to be 0.35. And as I'm looking back and reading this, I realized that I forgot to write the entire problem. Sorry about that. I wanted to know the rate at which the radius is increasing at the moment when the diameter passes 6 feet, at the moment when the balloon is approximately the size of me. Well, if the diameter is 6 feet, that means that the radius is going to be 3 feet. And again, the rate of change of the radius is the thing we are looking for. So just plug those things in. 0.35 is 7 over 20. So I can write that as 7 over 20 times 4 times pi times 3 squared, which is going to be 7 over 720 pi. All right. If you are so inclined, you can grab a calculator from here and you can get a decimal value out of that. I don't have a calculator at hand, so I'm not going to try. I can look at that and say that that's going to be about 1 over 300 or 1 over 350. 1 over 100 is 0.01. Divide that by 3, and that's 0.003. So somewhere in the range of 0.003. The units here, well, we've dealt with feet and cubic feet. We've dealt with feet and cubic feet per minute. So it looks like our length units are feet, our time units are minutes. So that would be 0.003 feet per minute. But again, I am actually happier if you leave it as the exact value with the fraction and all that fun. All right, so that's kind of the harder type of problem. I say it's harder because the formula isn't given to us. We have to know that the thing of interest is the relationship between volume and radius. Those things are both functions of time. And then once we write down the formula that we know from geometry, we can differentiate implicitly. It's a lot easier when a formula is given to you. An environmentalist has modeled the seasonal fluctuations in jellyfish populations as P of t equals 3 times the sine of pi t over 6 plus 1/8 times t minus 3 over 12, where P is measured in hundreds of jellyfish and T is the time measured in months since January of 2019. Would we expect the population to be increasing or decreasing in July of 2027? I would like you to take a couple of minutes and think through this problem, see what you can come up with on it, write out your solution, and I'll see you in the next video.